Hello, my name is Juhan Park. Today I will introduce a paper called LL3DA, Visual Interactive Instruction Tuning for Omni 3D Understanding, Reasoning, and Planning. The paper was accepted to CVPR 2024. Nowadays, large language models are applied to a wide range of tasks including coding, vision language understanding, and planning. They demonstrate strong performance thanks to their generalized reasoning abilities. However, a major limitation is that they lack the 3D spatial reasoning capabilities. This shortcoming significantly hinders progress in fields such as embodied AI agents, AR/VR assistants, and related applications. While numerous studies have attempted to address this limitation, each comes with its own drawbacks. Many LLMs are trained as domain specialists, making them unsuitable for general-purpose tasks. Some approaches integrate 2D feature maps extracted from multi-view images to enable 3D understanding, but this incurs substantial computational costs and often overlooks explicit geometric and depth information. Other methods incorporate 3D geometry directly into the LLM, such as using point clouds. However, these methods typically focus on object-level understanding and fails to perform complex scene-level reasoning. Today's paper presents a large language 3D assistant framework designed to overcome these challenges. It employs a multi-modal transformer that encodes both 3D scenes and user interactions into LLM interpretable representations, enabling effective spatial reasoning. The paper formulates its problem setup as follows. The model takes three types of input. First, a point cloud that represents the 3D scene, each point containing its XYZ coordinates, along with extra features including color, surface normals, and height from the nearest ground point. Second is a text instruction, which goes like, what is the color of this object? And third is visual interactions, which can either be a single point in the scene or a bounding box that surrounds a certain area. Using these inputs, the model generates a free-form natural language response. The instructions are written in a dialogue format where the human asks a question and the assistant replies. This design allows for smooth, multi-turn conversations between the user and the agent. To feed visual interactions into the LLM, the authors convert them into plain text. Points are expressed as XYZ coordinates using a LOC tag, while bounding boxes are described by their center point and size using an OBJ tag. Before passing this data into the LLM, all data points are quantized into discrete unsigned integers. This makes the 3D coordinates more LLM-friendly, allowing the model to handle them without having to learn new tokens for representing floating point numbers. Here we look at the overall pipeline of their method. It consists of three main modules, an interactor 3D, a linear layer, and the LLM. The interactor 3D takes the visual prompts, textual instructions, and point cloud and combines them into a fixed-length scene embedding. The linear layer then projects this embedding into a prefix that is attached to the front of the text instruction. Finally, this prefix, along with the instruction itself, is fed into the LLM to generate the response. Now let's get into the details of their method, starting with the interactor 3D. This module is made up of several components to aggregate the point cloud, visual interactions, and text instructions. The scene encoder is responsible for embedding this point cloud. It's a mask transform encoder pre-trained on the ScanNet dataset and is kept frozen during training. The point cloud is first reduced from n points to m points using the furthest point sampling algorithm. The sampled points are then passed through the scene encoder to produce the final scene embeddings. Next is a visual prompt encoder, which processes the visual interactions. As mentioned earlier, there are two types of interactions, clicks and bounding boxes. A click is generated when the user selects a point in the scene. Its XYZ coordinates are normalized to a range between 0 and 1 based on the scene's size, and then passed through a 3D Fourier positional embedding function. A bounding box, on the other hand, is represented as a region of interest feature extracted using a pre-trained 3D object detector. Both the click and the bounding box are then projected using feed-forward networks with separate networks for each type of interaction. The multimodal transformer brings all of these processed inputs together into a fixed-sized embedding vector. It does this using a learnable query vector, which acts as a container to combine the different data sources. The transformer is made up of several blocks, each containing a self-attention layer followed by a cross-attention layer with feed-forward networks at the end. The self-attention layer enables interaction between the learnable query tokens, the visual interactions, and the text instructions. The cross-attention layer then allows the query tokens to interact with the visual tokens and the scene embeddings. After passing through all transformer blocks, a final linear layer projects the final output into the LLM's word embedding space. The LLM receives this as the prefix for the text instruction to generate a response. In addition to this model architecture, the authors introduced instruction tuning to enable the LLM to handle a wide range of tasks, something that previous works on specialized agents struggled to achieve. To achieve this, the authors designed specific instruction patterns for each target task. For some tasks, they even create multiple formats to improve the model's robustness, allowing it to handle different question styles that lead to the same answer. For example, in the task of 3D dense captioning, which requires the LLM to locate an object in the scene, they provide two formats, describe and localize. As shown in the below image, when the user asks the LLM to describe the sofa in the image, the query can be phrased in either of these two ways. To evaluate their method, the authors conducted a wide range of experiments. They used the ScanNet dataset for 3D scenes with language annotations sourced from ScanRefer, Anner3D, ScanQA, and 3D-LLM. The LLM's responses were assessed using standard language evaluation metrics including CIDR, BLU4, Meteor, and RougeL. The first experiment compares their method with state-of-the-art specialist models on 3D dense captioning. In the results table, the number shown to the right of the @ symbol represents the threshold for how closely the generated bounding box matches the ground truth box. If the correspondence falls below the threshold, the model receives a score of 0. We can see that across almost all cases, their method achieves the highest scores. The second experiment tests performance on 3D question answering tasks. Some models are marked CLS, meaning they get to choose answers from a predefined set of options. The evaluation is done in two settings, with objects, where visual interactions like clicks and bounding boxes are provided, and without object, where the model must answer based only on the text. In most cases, the proposed method delivers the best performance. The authors also conduct ablation studies to validate their architectural choices. The first examines the effectiveness of the Q-former design, where visual prompts are integrated with text instructions through the multimodal transformer rather than being passed directly into the LLM. As shown in the chart, this early fusion approach achieves significantly better performance than the direct injection approach. The next ablation study tests whether adding extra instruction formats and visual prompts during training benefits the core tasks. Oxlock indicates whether the model is trained with detect and localize instructions, while clicks indicates whether clicks were included as additional visual prompts. The results show that performance is highest when both extra instruction formats and visual prompts are used during training. The generalist experiment evaluates whether the model can distinguish between different tasks based on textual instructions and visual prompts. The first 3 rows show the performance of models trained from scratch on a single task, while the next 3 rows show fine-tuned models. The final row reports direct evaluation without any fine-tuning. The results demonstrate that the model can successfully differentiate between 3D dense captioning and 3D question answering while achieving strong performance. The third study examines whether text instructions are necessary for 3D dense captioning. The results confirm that including text instructions lead to better performance. The final study investigates whether providing clicks on relevant objects alongside textual instructions during evaluation improves performance in 3D question answering. The results show that it indeed provides a performance boost. Thank you for your attention. If you have any questions, please leave them down in the comments.